Hello, welcome everyone. Uh, Thanks for joining this DLI session on accelerated workflows for generative chemistry and predictive modeling. I'm Neil Patel. Uh, if you guys can hear me and if the screen looks okay, please can somebody confirm in the chat? All right, it looks like we are good. Thanks again, everyone, for joining. My name is Neil Patel. I am a technical marketing engineer at NVIDIA. I work in the Clara drug discovery team. And today I'll be joined by my colleagues, Miriam and Rajesh, uh, who are also members of Clara Healthcare. And before we begin, I just wanted to make sure that everybody has the node, the lab instance up and running. If not, you can go to the links that are provided in the chat to start the lab instance, and you'll need to enter the event code. Please also note that the event code is only valid for the live session. So if somebody is watching the recording later, it won't be valid. So please uh, go to the link and start your instance. Okay, so while everybody gets uh, the instance up and running, I will spend a few minutes to just give some background on what large language models are and how they can be useful in the chemistry uh, for either molecule generation or for predictive modeling. So in the first few minutes, while everybody's uh, getting ready, I will go through some of the slides just to give some background for folks who are not too familiar with the recent advances in the field. Okay, yeah, so as I begin this uh, background, I just wanted to mention that NVIDIA has a Clara discovery uh, that is focused on advancing, accelerating drug discovery and healthcare. There are several open source as well as commercial tools that are accelerated using GPUs, which are also hosted on NVIDIA's NGC repository. You can go to this link that is provided at the bottom of the slide and find out more about the containers or tools that are available. And they range and they cover a wide variety of areas of early stage drug discovery. For example, there are tools for cryo-electron microscopy. There are tools for molecular docking and molecular dynamic simulations. And there are also tools to accelerate genomics pipelines and bioinformatics workloads. Uh, so please go and check these links if you're interested in finding more about GPU accelerated tools available through NVIDIA NGC. Okay, so moving on, this just a brief background on drug discovery process. So drug discovery itself is a time-consuming and very expensive process. It takes often 10 plus years to get a molecule from initial stages to all the way into clinic. And it's a $1.2 trillion industry and takes about $2 to $3 billion in R&D costs uh, per drug. And there is a high failure rate. It's about 90% failure rate. So at NVIDIA, we are focused on developing tools that can help accelerate the early stages of drug discovery and that can help the overall expedite overall the process. And NVIDIA has some of the prominent uh, Inception partners that are working in expanding on that frontier and helping with the drug discovery process. So the focus of today's lab is using a large language model called MegaMolBART and using it for early stage drug discovery. So basically either finding new chemical matter or using the chemical space that someone has to learn from it and to make prediction models. So very briefly, what are large learning models or large language models? So basically, the in the past half decade, there are advances that happen in the way we process large corpus of data. So the data could be text data or image data, and a new architecture called transformer that was discovered that can use the data and learn from it in a self-supervised manner. So you don't need to provide instructions or you don't need to specify what to learn. It sort of breaks down the large course data into small tokens, and then it learns from the relationships of how the tokens uh, are are related with each other, and then it sort of in that way it learns the relationships uh, for example, in the language or in any data uh, that that's there in the textual format. So what this large language model does is it takes the data, ingests the data, learns from the data in its encoder and decoder architecture, and then we can use these components to either predict what the next sort of token would be in the data or what uh, the underlying patterns are in the corpus of data. So initially, these techniques were applied for, as I mentioned, textual data from the internet web pages. But later on, uh, very quickly, it was also applied for generative chemistry for predicting protein properties and for biomedical natural language processing and image analysis. So in today's lab, we will discuss megamolBART. So what megamolBART is basically is a large-scale pre-trained transformer AI model. And I'll briefly discuss what transformer architecture is. Uh, so this model is basically trained on SMILES. SMILES is a one-dimensional sort of chemical representation format. Once a smile is shown here for a molecule, and it basically captures how the atoms are or how the constituting atoms are linked in the chemical structure. And basically, we can feed the smiles the same way we can feed any text data to these large language models and learn the relationships among the tokens that are there constituting the smiles. And we can use these large language models to basically explore vast chemical space. Okay, so like I was mentioning, the main goal for this large language model, megamolBART, is to expedite initial stages of drug discovery. So either uh, you're looking for a hit against a protein target, or if you have some initial hit compounds or fragments, if you're looking forward to optimizing around that scaffold, you can use uh, these large language models either for generative chemistry, and you can also use these large language models to extract its latent embedding, latent space representation, and use it to generate a prediction model. And why this chemical space exploration is important, because the estimated drug-like chemical space of small molecule is huge. Estimates are anywhere between 10 to the power 25 to 10 to the power 60 compounds. And there is no practical way to store such a huge database and explore it in an efficient manner. So if somebody has a hit compound and they want to find what are the similar analogs in the database of such size, uh, it may take years or more with the existing computing power to explore through that space. So even currently available exhaustively enumerated libraries such as Zinc or InnovenReal, they have compounds uh, in the billions. So these libraries have billions of compounds, and it is also challenging to explore these libraries that goes into billions or tens of billions of compound size. So there are alternate ways that are needed to explore the vast possible chemical space. And also there is a need to learn how the chemical space is sort of oriented and how we can use it for hit finding and lead optimization. Yeah, so this is sort of a conceptual overview of what we are doing. So we are learning from a chemical representation that's shown to the left of the encoder. We are passing the chemical data in in a way in a smiles format. What the encoder does, it breaks down into its constituting tokens and learns how the tokens are are sort of represented and what their underlying relationships are. So it takes this smiles representation and takes it into a higher dimensional latent space where these tokens or the relationships are captured, and then we can use decoder to sort of decode what the latent space representation is from the latent state representation to its smiles representation. So basically, we can regenerate the chemical representation. And again, this is like a very simplistic example of what goes on. So folks who are not familiar with uh, how these large language models are sort of they perform. So on the left, I am showing what happens with the textual format because it's easy to relate. So for example, here we have one-dimensional text input, right? So it could be a string, it could be a string of words, sentences from a book. So the model ingests a sentence, tokenizes it, and then what tokenization means is it gets a value or a token assigned for each word that's there in the dictionary. Now, once we have tokens, we can do several interesting things, right? We can mask a specific token and then ask the model to predict what a possible token is. So what the model will do is it will try to provide multiple options, right? It could be green. So in this particular case, the grass is green. It could be brown. So different possible tokens at a given place with different probabilistic values. So the model will try to predict, and then it's an iterative learning loop. So for different sentences, different tokens, it will try to predict what's there and what's the next probable token. Similarly, for a chemical data, right? So we can represent the chemical data as 3D sort of object in a computer. We can also represent it as a 2D graph or 2D image of a molecule to show how atoms are linked with each other. We can also show it as 1D smiles format. And once we supply the smiles format, we can mask some of the components or the tokens in the smiles. And then we can ask the model to predict what could be a valid atom or valid token that can fill that mask position. And the model will learn iteratively from the chemical data set. So like I was mentioning, there was a breakthrough that happened